Now, my dear students, work done is stored as potential energy. Charge move from one point to another point because of potential difference. So, potential energy is what? Stored energy. Work has to be done to transfer charge from one point to another point. And that work done is always potential difference into charge. In this difference in potential, final point and initial point, V final minus V initial into charge. And this work done is always stored as potential energy. It is denoted by letter U. You can write PE. Stored potential energy is potential difference into charge. Work done in transferring a charge from one point to another point is stored as potential energy. Now, we have to derive formula, that is potential energy due to system of 2-point charges, that is 1 by 4 pi epsilon naught into Q1 Q2 divided by R, due to system of 2-point charges, say Q1 Q2 separated by distance R. The stored potential energy is 1 by 4 pi epsilon naught Q1 Q2 by R. To derive this, the basic idea is this. But here they say that in the absence of electric field, means initially no electric field exists, nothing exists, empty, nobody is there. Get the expression for potential energy. To measure potential energy, we told that we should choose some reference point. To measure potential or to measure some potential energy at a point, we must take some reference where the initial potential is 0 and the electric field is also 0. This is possible only at infinity. At infinite distance, potential and the electric field are 0, which is taken as reference point. From this reference point, we start moving the charges and work done by the charge. Work done in carrying a charge either by electric field or on the charge. Work done by the charge or work done on the charge by the electric field is conservative. Electric fields, magnetic fields, spring energy or spring force and the gravitational force or the gravitational field, they are conservative in nature. Means they do not depend on the path how you carry. Let me explain this. Say I have a ground where the initial potential energy is 0, potential is 0, which is taken as a reference. And let us say I have to carry a box to, say, 3rd floor of our college. One man will carry like this, A. B will carry like this. Third will carry like this. Means in different path. Here height remains same. From the ground, all the 3 persons are carrying the object of certain mass to the 3rd floor. Height remains same here. All should carry the box to the 3rd floor only. One is straight, another one is taking a path along the staircase, other one is random, curved path. Now among these 3, which one has done so more work here? Can you say C? Can you say B? Can you say A? Of course, what the person who is carrying the box along A, along B, along C is same. Does it remain same? No. But work done by the gravitational field. Work done by the gravitational field, not by the person. Work done by the gravitational field does not depend on the path. For all the three persons, the work done by the gravity is same, does not depend on path along which they move. Path independent. So like that, to carry a charged particle, we need some work here. We need some work. And that work done in carrying a charge in an electric field does not depend on the path. It depends only on the initial point and the final point. Such fields are called conservative fields. With that basic knowledge, now I have a reference point from which I am carrying the charge Q1 from infinity to the point of conservation. This zigzag path, you must feel that it can be carried in any path. Does not depend on the path. Work done by the conservative field does not depend on the path how you carry. Depends only on the initial point and the final point. This is the final point now. Now this charge is carried from infinity to the point. Let us say Q1 has occupied some space here. Now they told in the absence of electric means when you are carrying, nobody is there. Nothing exists. Means your potential is zero. Electric field is also zero here at this point. So what is work done? Potential difference into charge. To understand clearly, I am explaining neatly. Follow this step. What is the charge now? Q1. Can you say what is the potential difference here? Initial potential is 0. Final potential is 0. Potential difference becomes 0 into Q1. So, no work done. In carrying a charge from Q1 from infinity to the point under consideration where electric field is 0. Now I have another charge Q2. It has to be carried from infinity to the point of consideration. I feel that Q2 has to occupy some space here. It should occupy some space, some position. Stored energy. It has to occupy some space means it has some position. And that energy possessed by a body or a particle by virtue of position is called potential energy. That stored energy is called potential energy. We are deriving that formula. Now tell me, for bringing Q1 initially no one was there. So electric field is 0, potential is 0, therefore work done is 0. Do you feel that Q2 is also experiencing no work? No, because at a distance say R, from Q1, is potential at this point is 0? No. Potential at this point becomes how much? 1 by 4 pi epsilon naught. Don't write Q2. Q1 divided by R. By the formula potential at this point because of this charge. What is the formula? 1 by 4 pi epsilon Q1 by R. Now this charge is carried now. It is occupying some space here. Again, path independent. What is the initial potential now? 0. What is the final potential here? Vf. Therefore, work done 2. In carrying a charge from infinity, in carrying a charge Q2 from infinity to the point of consideration, so potential difference into charge. Potential difference, V final minus V initial. V final is this, 1 by 4 pi epsilon naught, Q1 divided by R, V final, minus 0. Potential difference V final minus V0 into the charge that is being carried, Q2. Have you understood, my dear students? This, just multiply. You will get it. Work done, WT is equal to, how much you will get? 1 divided by 4 pi epsilon naught, Q1 Q2 divided by R. Now what is the total work done in assembling how many charges? 2 charges, that is Q1 and Q2. Now they have occupied some space here. So energy by virtue of its configuration, energy possessed by the charged particle by virtue of their position is known as potential energy. Therefore, total potential energy I can write sum. That is total work done. Total work done in assembling the charges is stored as potential energy. W1 is how much? 0 plus 1 by 4 pi epsilon naught. So simplify. Now you get total potential energy is 1 by 4 pi epsilon naught Q1 Q2 by R. Understood? This potential energy is expressed in terms of unit joule. Again, work done is a scalar quantity. Potential is a scalar quantity. If you have any one charge negative, say Q1 is positive, Q2 is negative, then you must write potential energy is 1 by 4 pi epsilon naught Q1 into minus Q2. If any one of the charge is minus, take the sign also. I think, have you taken this? Let me study the same concept for tree system of point charges in the absence of electric field, where no electric field exists. As we studied, question is expression for potential energy due to system of 3-point charges. Initial is 0, V initial is 0. This is taken as reference now, reference point. Now I have 3 charges now, Q1, Q2 and Q3. As done earlier, so from infinity to the point under consideration, no electric field exists. As we studied earlier, work done becomes 0. Again, in carrying a charge Q2 from infinity, say to the point of consideration, how far? Say R1, let us say R1 from Q1. As we studied earlier, potential is not 0 here. This potential at point is equal to 1 by 4 pi epsilon naught Q1 divided by 1. Q1, not Q2. Initial is 0, final is 0. We have done the work that is equal to, for system of 2 charges as done in the previous, 1 by 4 pi epsilon naught Q1 Q2 divided by R2. This is work done for bringing Q2 from infinity to the point of consideration. How we got? You can refer the previous derivation. Now the thing is, extra is, I have to carry the third charge, say from infinity to here. Let us say here. How far? Let us choose this point as R2, R1, R2, and from here to here, let us say it is R3. Have you got this idea now? Now the Q3 has brought now, Q3 is brought from infinity to the point of consideration. Earlier when you are bringing Q1 here, there was nothing. Work done is 0. Second, stored as potential energy. Now, because of these two charges, now you will have some new potential at point 3. That is due to first charge and second charge. Point 3 surrounded by how many charges here? 2. Therefore, potential at point 3 is the sum 1 by 4 pi epsilon naught Q1 divided by how much distance it is? R3 plus what is another potential at point Q3 by this charge? That is Q2 divided by what is the distance here? R2. You got 2 potentials here because of these 2 charges. So now final potential at point 3 is how much? V3. This is V final at point 3. What is the initial here? Vi. Therefore, work done, third work done in carrying a charge Q3 from infinity to the point of consideration. Again, potential difference into charge. What is the potential difference? V final minus V0. V final minus V initial. What is the charge that is being carried? Q3. V initial is 0, V final is this. So for this you have to multiply it by Q3. So now work done, W3 will be is equal to, for this entire thing, multiply by how much? Q3. Now I rewrite this, 1 by 4 pi epsilon naught, Q1 Q3 divided by R3 plus Q3 into Q2 divided by R2. I think understood this. Now, how many work done now? Total 3. W1, W2, W3. In assembling, how many charges? 3 charges. So, therefore, the total work done that is stored as what? Potential energy. W1 is 0 plus this and this. You have to add these two. What is the common here? 1 by 4 pi epsilon, 1 by 4 pi epsilon not common. I jump one step over here. Sorry, for this it is R1. No mistake, Q1, Q2 by R1 by R1 plus, what is the second step? Q1, Q3 by R3 plus, what is the last step? Q3, Q2 divided by R. I think you understood this. Now final, you can memorize all the two formulas. If derivation is asked for 3 marks, you have to follow this step. Now, I repeat the same formula. Potential energy due to system of 2-point charges in the absence of electric field. And that work done is stored as potential energy given by the formula 1 by 4 pi epsilon naught Q1 Q2 divided by R. Which is expressed in terms of unit joules. This is for system of 2-point charges. For system of 3-point charges, 1 by 4 pi epsilon naught, I give a small help for you. Take a triangle, Q1, Q2, Q3. Need not be a triangle. This Q3 may be over here also. You can put Q3 here also. Okay. Now, Q1, Q2 separated by R1. These two separated by R2. These two separated by R3. Take it in a cyclic order to memorize the formula. Q1, Q2, Q3. Cyclic order, either anti-clockwise or clockwise, your convenience. Q1, Q2, Q3. I have taken in anti-clockwise direction. R1, R2, R3. 1 by 4 pi epsilon is common. You must have product of two charges. Q1, Q2, 1, 2 divided by R1 plus 2, 3. Q2, Q3 divided by R2 plus 3, 1. Q3, Q1 divided by R3. And derivation at the same answer both. So again, this is expressed in terms of joules. For 3 marks, if the annual paper they ask, follow this step, or else memorize the formula for your competitive papers. Now let me solve one problem based on these formulas so that you will be of confidence in achieving these formulas. Why you have to learn this? Question is, I have to assemble, I have to gather some charges. They should occupy some space. When they occupy some space, by virtue of their position, they possess certain potential energy. And that stored energy we call as a potential energy. Now, let me solve one problem for you purpose. Say, question is this. I told earlier, all these need not be look like a triangle. So I give an example here. So let us say plus 2q, plus 8q and q. Two extreme charges are larger in magnitude and let us say this distance is 9 centimeter and this distance is say 3 centimeter. Question is, due to system of these 3 point charges, calculate the potential energy. ಏನಪ್ಪ ಅಂದ್ರೆ 2q is carried from infinity to this point. When no electric field, work done is 0. Then q2 is brought from infinity to the point under consideration. Work done 2. Work done 2 here, sorry. Then third charge, q is carried from infinity to the point under consideration. I repeat, all the 3 charges need not be in cyclic order. You can remember, they can come in the straight line also. Apply the same formula. Okay? Can you do it? Can you give me the answer? Have you tried it? How many charges are given? 3 point charges. So for system of 3 point charges, total potential energy is 1 by 4 pi epsilon naught into, I think you understood this, I will write in a fast manner. Okay? Q1 into Q2, 2Q into Q, divided by R1, divided by R1. Q1, Q2, Q3, Q2 into Q3, Q into 8Q, Q into 8Q, 9 minus 3, how much you will get? 6 centimeter, 6 centimeter plus Q1, Q2 ayatappa, Q2, Q3, then last Q3, Q1, 8Q into how much? 2Q divided by, what is the separation between last extreme charges? 9 into 10 to the power of minus 2. So now you can simplify according to your speed. 9 into 10 to the power of 9, q squared is common, divided by, in the denominator you can take 3 into 10 to the power of minus 2 as common. In the numerator also you can take 2 common. So what is left now? Q square is gone, 1. 2 outside, q square, 1 plus 2 is taken outside, how much you get? 4 divided by 2 is taken outside, 8 divided by 3 is taken outside, how much you get? 3. So your answer, 9 2s are, 3 1s are, 3 3s are, 6 into 10 power 11. 10 power 11 q square. What is the LCM here? 2 1s are, 2 2s are, you can take. How much you get? 1 plus 2. 3 plus 8 by 3. Do your mathematics according to your speed. I told many times. 11 q square into, what is the LCM here? 3. 3 3s are 9. 9 plus 8, 17. So 3 1s are, 3 2s are. 17 2s are 54 into 10 to the power of 11 q square is what? Potential energy stored, which is expressed in terms of joules. I think you understood this. If it is fast, again pause it, you can recall. Better you solve without looking at the solution after learning the concept. Now second question is this. There are 3 point charges, plus Q, and capital Q, placed at 3 corners of an equilateral triangle. 3 corners of, not equilateral, sorry, isosceles right angled triangle. Means these two sides are same, angle is 90, of course these two angle become 45. Question is, find the relation between Q and Q. Relation between capital Q and small q such that the total potential energy of the system is 0. Total potential of the system is 0. Just pause and solve it. Now, again concept is Have you tried it? I write for your easiness. So for a system of 3-point charges, let me do in fast way. 9 into 10 to the power of 9 common into Q1, Q2, Q square divided by A square. Taking cyclic order. Capital Q into small q divided by A, that is A root 2. Pythagoras theorem. A root 2. See here, not square. Q1, Q2 by A. Q into Q by A root 2 plus Q into Q. Q into Q divided by A. What they have given? The total potential energy of the system is 0. Obtain the relation between Q and Q. Means once it is carried to the right side 0, A 0, small q is 0. So what is left now? Small q plus capital Q by root 2 plus capital Q equal to 0. A is taken out 0. Small q 0. I think you understood this. Now I take this at one side. Q. What's the LCM here? Root 2. 1 plus root 2 equals to how much? Minus q. So therefore q is equal to, take it to the right side, minus root 2q divided by 1 plus root 2. In entrance papers you will get such a problem. In some papers they may differ the answer. Say here root 2q divide 1 plus root 2. What they do is multiply and divide numerator by root 2. This is what I am giving extra for you. Out of 4 options, if it is there, it is your goodness. Sometimes what the people do is, some mathematical peoples will do that, multiply and divide by root 2. Just to check the mathematical knowledge of a student. Root 2 is 2. So minus 2q divided by, multiply here, root 2 into root 2 is 2 plus root 2 into root 2. 2 plus root 2. So out of 4 options, you may get this or you may get this. I think you understood the formula of potential energy of 3-point charges when no electric field exists. Now, you can take that. Expression for potential energy for system of 2-point charges in the presence of electric field. Means stored energy for a system of 2-point charges, say Q1, Q2, separated by certain distance. But these charges has to be carried against the electric field. Means there is presence of electric field. Initially, electric field is not equal to 0, means some electric field is there. Means, say, there is one source charge, source. This source charge Q is producing some electric field. There is some electric field. I have taken some reference here. So if I place a charge here, say this Q1 has to occupy some space here. It has to occupy some space. How far? Let us say it is at a distance R1. From which charge? Source charge. Means Q1 has to carry it from infinity. That reference point is infinity. This charge Q1 and say Q2 has to be brought from infinity, where potential and field are 0, to to carry this charge from infinity to the point. Say this is the point of consideration. Now is this electric field is zero? No. This source charge will produce some potential at point. Let us call this as potential at this point at a distance r1. V of r1 andre potential at this point at a distance r1 from Q. Do you feel that potential is zero? No. Because of this charge, some field is there, and in work done carrying this Q1 charge from infinity to this point will store as some potential energy. Therefore, work done is W1. Work done in carrying a charge Q1 from infinity to the point where electric field exists. That is potential difference into charge. Can you recall what is this potential? V initial minus V final. Potential difference. V final minus V initial. I write V of R1 into Q1. Similarly, can you give me the formula for W2? Just as we done here. Now let us say I have to bring Q2 so somewhere here. Dotted means you are carrying from infinity here, just to represent. And again I am repeating this style. You can say the path independent work done by a charge. Work done in carrying a charge by the electric field does not depend on path. Depends on the final point and the initial point. Such fields are called conservative. We are doing with work done in a conservative field. Therefore path independent. So what is the final position here? Do you feel that potential is zero? No. This charge will produce some potential. This also produce some potential. So there is some net electric field. Let us say that is VR2. Some potential will be there because of this charge and because of this charge. Both charge will produce some electric potential. How much? Let us imagine that of how much it is VR2. Therefore, work done in transferring Q2 from infinity to the point under consideration is again potential difference. V final minus V initial. V final, V of R2 into what is the charge that is being carried? Q2. Understood? But as soon as when you bring this Q2 from here, this Q1 and Q2, because of their separation, certain separation, they also possess certain potential energy. Therefore, that work done for assembling how many charges? 2 charges. Because of these separated by certain distance, they again possess certain potential energy as we derived potential energy due to system of 2-point charges. 1 by 4 pi epsilon naught. Q1, Q2 divided by, what is separation here? R. W1, W2, W3. Now can you tell what is the total work done in bringing Q1, Q2 from infinity to the point under consideration where there is a presence of electric field? And that total work done will be equal to W1 plus W2 plus W3. Just all of you arrange this. How much you will get? That is equal to, I write that side, that is equal to V of R1 Q1, V of R1 Q1 plus V of R2 Q2 plus 1 by 4 pi epsilon naught Q1 Q2 by R. VR2 Q2 ಅಂದ್ಕೊಂಡಿರಪ್ಪ ಮತ್ತಿದನ್ನ VR1 Q1 ಅಲ್ಲ ಇದು V of R1 ಅಂದ್ರೆ potential at this point at a distance R1. Okay, this is how you may get for 3 mark also. Write the expression for potential energy, stored potential energy due to system of 2-point charges in the presence of electric field. I think you understood this. Just memorize this. Copy ಮಾಡ್ಕೊಳ್ಳಿಪ್ಪ. In the previous discussion of effect of dielectric on the external electric field, we studied that the amount of the strength of electric field is reduced. That is F naught by K. Force is reduced. The amount of strength of electric field, applied electric field is reduced, and the potential difference also reduced. But I said the capacity will increase. This you will study in detail. On placing dielectric material, what is going to affect? How does dielectric is going to affect the force on a charge? How this electric field is going to be reduced? And how the potential difference is going to be reduced? And the induced charge due to dielectric polarization, we have proved this in the previous videos or in the previous classes, where K is dielectric constant, and that dielectric constant is always defined as the new force F dash divided by F. F naught divided by F dash. F naught is initial force before placing dielectric media. F dash, new force after placing dielectric media. This is also taken as E naught divided by E dash, which has no unit, no dimensions. All this has been discussed now. Now, so there is a conductor. Conductor is one in which free electrons are abundantly available. It contains free electrons. So when you apply some external field, we have studied this. By themselves, the free electrons inside the conductor, they align on one side and positive charges on the other side, such that the applied electric field direction and the induced electric field E naught and EIN, they become equal, opposite cancels. Therefore, electric field inside the conductor when placed in external field is zero. For a conductor, whether it is a solid conductor or hollow conductor, the electric field inside the conductor is zero. And by Gauss law also, if you have studied application of Gauss law for a spherical shell means empty inside the space. When you take a spherical shell, when you give a charge to a spherical shell, they are all what? Excess charges. I told excess charges which are being transferred from another body. If you observe a conductor is electrically neutral. You have electrons and protons. Electrons are negatively charged, protons are positively charged. They are equal in number, atomic number of electrons revolving around the nucleus, or the number of protons present inside the nucleus. They are equal in number. Protons are positively charged, electrons are negatively charged, and the total charge of electron and the total charge of protons is equal, opposite, cancel. The net charge of an atom is zero. Therefore, every conductor is electrically neutral. Means these charges are excess charges which are being transferred from other body to this. They all reside on the outer surface. If I take a Gaussian surface here, this dotted mark is Gaussian surface. Does this Gaussian surface enclose any charge? Do you get any charge inside the Gaussian surface? No. That inside you get 0. If you apply that electric flux what you have studied, E dot ds equal to Q inside divided by epsilon naught. I feel you are very familiar with this. E is into ds. E into ds. Some area you may get here. You may get some area. Some surface area you may get. So let us say E into that area. How much? Some value you will get. Does this Gaussian surface any charge inside it? No. So that becomes 0 by any number is 0. Therefore, electric field inside the charged spherical is 0. And also inside the solid conductor. I repeat, solid conductor. Without any fear, just write down E is equal to 0. If they give, for this conductor, when electric intensity is 0, as we know that E is equal to minus dV by dr. This is already explained. For a competitive, it is very essential. That is why I am repeating you. For a spherical shell, or a solid conductor, for a spherical shell or a solid conductor, inside the charged conductor, electric field is 0. So now you calculate this, dV is equal to 0 multiplied by anything is 0, integrate, you will get integration of 0 is constant. Means if you have a solid conductor or a spherical shell, you must write E is equal to 0, V is not equal to 0 and V is constant. V is not equal to 0 whether you take spherical shell or a solid conductor. For a charged spherical shell, I said shell, or a charged solid conductor. Be careful, my dear students, about these discussions. When a point of consideration lies outside the shell, let us say R. Front field R is a radius, distance from center. And of course, let us say this spherical shell of radius R, this radius R. By Gauss law, we have derived that electric intensity at this point is 1 by 4 pi epsilon naught, the charge, let us say Q, divided by distance from the center is R square. If they give a solid sphere, when point P lies outside the solid sphere, you must feel that the entire charge which resides on the outer surface, I repeat, excess charges are residing on the outer surface. Inside the solid conductor, E is 0. Here also E is 0. When point lies outside the surface, you must feel that this solid sphere is a point charge. This entire charge is replaced by a single charge Q at a distance of R from point P. Write the same formula. Have you understood? For a solid sphere, these all excess charges resides on the outer surface. By Gauss theorem, we have derived it. Taking the same concept, no need to derive here. You must feel that you have to take this I am repeating the same word. This solid sphere, when charged, no charge exists inside the conductor. E is equal to 0. All these charges are excess charges which are being transferred from some other body or some by battery. When it is charged, the potential at point P is 1 by 4 pi epsilon q by r square. This formula tells you that the entire charge is deposited at the center. And as we studied, potential is constant. And that potential is equal to the potential on the surface of the conductor. And as we studied here, we have studied E is equal to 0 means, and E is minus dV by dr, and dV is equal to minus E into dr. This potential difference is 0. On integrating, we got V is equal to constant, which is same as that on the surface. Means, just to take the point P, let us take the point P on the surface. In the previous video, I have derived the formula, just go through that. Potential on the surface is given by the formula on the surface, that is R is equal to R. When point P lies on the surface, this is the formula. Whether it is a spherical shell or a solid conductor. Now inside, if I take a conductor here, potential is V. So let us choose at the center some points you can take, A, B, randomly you can choose. Wherever you want you choose. Now what is the electric field inside the conductor? 0. When electric field is 0, potential difference is also 0. When electric field inside the conductor is 0, potential difference is also 0. Means in this point, if we choose any 2 points here, if it is of V volt, it should be how much? V. So that the difference in voltage should be equal to how much? 0. I think you understood this. Whether it is a spherical shell or a solid conductor, inside the conductor, inside the shell, electric intensity is 0, potential is constant. Graphically, you have to represent both variation of electric intensity and potential. Can you draw it?